This is a brief introduction on cosmological inflation, and we're going to start with the Big Bang and its successes. The Big Bang theory has successfully predicted the expansion of the universe, the existence of the CMB and its power spectrum. It accounts for the abundance of light elements like hydrogen and helium, and it makes reasonable claims on the age of the universe, which fits well with how old we believe many astronomical structures to be. Furthermore, the existence of fluctuations in the CMB suggests the possibility for a structure formation mechanism. However, this model's success only holds true for a very specific set of initial conditions. Next, we'll look at some of the theory's shortcomings. There is the flatness problem, where the deviation from flatness is given by this equation with c set to 1. As the universe expands, the scale factor and Hubble constant push the energy density away from 1, so you'd expect the curvature to make a minute contribution over time, since we measure a flat universe today. However, we see the curvature redshifts away more slowly than radiation or matter. This presents a fine-tuning problem. There's the horizon problem, which stems from the fact that the observed CMD is isothermal with the same statistics in every direction, which is strange considering information transfer is limited by the speed of light. Opposite sides of the universe are out of causal contact, and the Hubble distance between time zero and decoupling is much less than what it would need to be to explain the universe today. So the fluctuations must be part of the initial conditions. Finally, there's the monopole problem. Modern particle theories predict the existence of magnetic monopoles and other relics like the gravitino. These are expected to have been created by high temperatures in the radiation era. They're thought to dilute as e⁻⁻3, which is slower than radiation, and should make them abundant in the universe today. However, this is not the case. These problems are the motivation for inflationary theory, which is most commonly represented as a scalar field model. It was responsible for the early expansion of the universe, stretching space-time from 1/4 the size of an atom to the size of a dime. This can be represented graphically by a ball rolling down a potential hill. Expansion occurs when the ball is on the plateau and ends partway down the slope. When it reaches the minimum, the potential energy of the inflationary field decays into regular matter and radiation. This is known as reheating. Some might say the theory of inflation is a hero. It has come to the rescue. It works well with the Big Bang model and resolves these inconsistencies. In the case of the flatness problem, inflation imposes the condition that the energy density is pushed to 1 with expansion as opposed to away from it. So 1 over the scale factor squared times Hubble parameter squared decreases in time. Graphically, the change in energy density over time is seen as a peak followed by a plateau. These 4 arrows indicate the beginning and end of inflation, where we are today and the distant future. The horizon problem exists because the Hubble length before inflation is much smaller than expected to explain the isothermality of today's universe. However, according to inflation, the Hubble length actually decreases while spacetime expands. In this diagram, the radii of the circles indicate the Hubble length in co-moving coordinates. Everything inside the golden circle is in causal contact and therefore isothermal overall. As you can see, inflation greatly decreases the Hubble length. Today it is much larger compared to the end of inflation, but our horizon still sits well inside the isothermal region. Finally, the monopole problem. It arises because magnetic monopoles and other relics dilute as e⁻⁻3, but the energy density during inflation falls off as e⁻² or slower, so inflation would be very successful in diluting the relic particles. This would account for the fact that these particles have never been observed despite their theoretical existence. However, there is a strict condition for this to hold. Since the creation of many of these particles requires extremely high temperatures, there are constraints on the allowed temperature of reheating to ensure the relics don't pop up again after inflation. At present, inflation is the most promising model for solving flatness, horizon, and monopole problems.